Hey, I'm Simon. It's really great to be part of the AWS Community Day. So today I'm sharing a project, how to sort my socks with an AWS DeepLens, answering that age-old question of, can I arrange my sock drawer using machine learning? So I'm Simon Aubury. I'm a principal data engineer at ThoughtWorks in Sydney, Australia. I'm here because I love technology and love playing with gadgets. And generally my day job involves building event-driven systems using combinations of IoT and event-driven architecture. So today I'm sharing a small side project that illustrates some of the problems and some of the solutions when you combine machine learning vision with event-driven architecture. So I'm going to be pairing socks with machine learning vision. Can I arrange my sock drawer using transfer learning? Ultimately, can I build myself a custom sock classification model? And can I use open source technology and streaming technology to retrieve those sock classification messages? So ultimately, can I take my unordered socks and build out nice pairs of socks? And to do that, I need to perform time series analysis to make sure that when I bring out classification messages, I can actually scrape back in time to find where I've seen a similar sock message before. Now, we'll be covering a lot of bits of technology today, but I wanted to point out that this source code is available online. It's open source at that GitHub link. So hopefully that gets you excited, but no doubt you've got also a bunch of questions. Maybe your first question is simply, why? What are you trying to achieve? That's a super good question. I get to see events everywhere. Event-driven architecture is super cool. It's this architecture paradigm that it's promoting the production, detection, and consumption and reaction to events. So event-driven systems are a very, very powerful and flexible way of building out technology. But object detection, at the end of the day, is just a stream of events. An event-driven architecture coupled with machine learning vision offers up a great way of seeing the world and processing some things in the real world. Let me give you some examples of both the problems and solutions that come together when you mate machine learning vision with event streaming architecture. So when I started this project, this was my naive idea of how machine vision worked. I was thinking that if you held up something in front of a good classifier, you'd get a nice clean image. So if I took a blue sock and held it in front of an image classification model, it should tell me that it's encountered a blue sock. Equally, if I hold up a green sock, it should identify that this is a green sock. So this was my mental model of how things would actually work. But in reality, things aren't that clear. In reality, what actually happens is if you hold up a blue sock in front of a classifier model, it might identify that in each and every frame. More confusing is when things move in and out of frame. So you might end up with several messages in a row, all indicating that it's seen a blue sock. But as things walk in and move in and out of the edges of the frame, you get these sort of aberrations, and I call them phantom messages. So after it's seen an orange sock and it's just leaving the frame, you might get these sort of phantom messages, and they might just be misclassifications, but they tend to be very, very short. So I've got a bit of a problem here. I want to be able to cleanly identify when I've got pairs of socks. But if I end up with 5 messages in a row, all indicating blue sock, that's going to really confuse my algorithm, and it's going to tell me I've got many more socks than I actually have. So what I actually want to do here is clean up this stream of messages and collapse down all of these similar messages. Maybe if I've got 5 blue sock events, one after another, I want to collapse those events down to just say, you have seen a blue sock. And if I've got these little like sporadic events, like just one white sock event, maybe that's a bit of noise and maybe I want to drop that out. So I've got a few problems to solve here. I want to be able to collate multiple identification messages together. I want to remove those random spurious phantom events and ultimately have a clean stream so I can perform some time-based processing and ultimately find my pairs of socks. So this is covering a lot of territory. So let's start at the end and we'll work backwards on how we got there. So this is what my classifier looks like. I can hold up a sock and it will make a relatively fast estimate on what sock it's seen. Now, I want to emphasize that once this project has been trained, this is a completely offline solution. There's no cloud involved once this model has been trained. So this is switched on and running in a completely offline mode. So let's walk you through this. I'm holding up a sock in front of the camera. A classification algorithm is running on every single frame that it identifies. A message is, once a classification has been made, that message is written to an MQTT endpoint. Those messages are then put onto a Kafka stream, and I'm then going to perform a level of stream processing on Kafka. That stream processing is both to clean up those messages, collapse down the multiple messages, and ultimately find where there's been a matched sock within the stream. So what I really want to know is if I hold up a blue sock and a green sock and another blue sock, I want to be able to mate the fact that the first blue sock and that third blue sock should be matched together. Now, this might seem silly, but you can think of this as scalable technology. The fact that I'm using one camera can actually be scaled up, and this exact same technology could be used for multiple cameras if you've got a household where you've got to match many socks together. So I've mentioned this a few times, that this is the actual camera that I'm using. This is called an AWS DeepLens. Now, this is very useful for someone like me. I'm not a machine learning expert, but a video-enabled camera that has a lot of the smarts on board really makes some of these complicated tasks of deploying edge-based processing much, much simpler and much more accessible. So this on board has a reasonable video camera, a 4 meg still and video camera. Inside, it's got an Intel Atom processor, it's got 8 gig of RAM, and ultimately it runs Ubuntu under the covers, so I can deploy my own packages. In short, it's got plenty of hardware to help me sort my socks. Now, I need to help firstly build out a classifier model to actually deploy onto the DeepLens so it can actually identify socks in the wild. And for that, I need to get myself some training data and prepare that training data so I can teach a model to run classification of socks. Now, to prepare that training set, I really need to take photos of socks. In fact, I need to take many photos of socks. With it, for my purposes, I found that between 30 and 40 photos of each sock help build out that classifier with a reasonable layer of confidence. And taking photos of socks is really as interesting as it sounds. So this is a great way of spending your Sunday night, building out many, many photos of similar socks. But ultimately, this is necessary to get a level of confidence in the classifier model. Now, I've mentioned this a few times. I'm building an image classification model, but how do you actually go about that? How do you actually train an image classification model so it can classify sock images? I'm using a mechanism called transfer learning, and at the end of the day, transfer learning just takes a general purpose classifier and helps it on its way to become quite a specialized model. So I can run all of this in a hosted Jupyter notebook, and AWS has a fantastic service called SageMaker. So I can write Python in a Jupyter notebook and help take some general purpose classifying models and actually use transfer learning to get them very, very specialized with my training data so they get very good at identifying my socks. So I'm using AWS SageMaker and building that image classification algorithm. I'm taking a general purpose classifying algorithm and using transfer learning to help hone it to get it more specialized for my training needs. Just to get level of confidence that my classifier is actually working, I'm just temporarily deploying it to a classifier in the cloud and running up just a few demonstration images that I've just stored in an S3 bucket, just to give myself confidence that the classifier is working. I'm just going to do this as an exercise in the cloud. And once I've convinced myself that the model is correct and accurate most of the time, I'm going to take that model and deploy it to the DeepLens itself. Now, I've actually got to run both a model and a bit of supporting code on the AWS DeepLens. And this supporting function is called an inference function. And although it's called a Lambda function, you have to remember it's a Lambda function that's running on the AWS DeepLens. So I'm going to run all images captured by the camera through this classification model. And in addition to getting classification messages and ultimately processed by a machine, I as a human also want to see what's going on. So I can actually point a web browser to the IP address of the DeepLens and get a live feed of what the camera is seeing. And I want to have a bit of text overlay on that video feed just to see what's going on. So I'm going to be using OpenCV, which is a C library, but it's actually wrapped in Python. That allows me to just do some really straightforward text overlays on that image. So when I'm viewing it in the web browser, I get a nice textual overlay of what's actually happening. In addition to seeing it in the browser, what I ultimately want to do is make sure that those classification messages are ending up in a machine readable place. So I'm writing them to an MQTT topic. So I've mentioned this Lambda function a few times. It's probably worth stepping into. I want to emphasize that this Lambda function is running on the AWS DeepLens itself, not in the cloud. So the first thing is I'm going to be getting an image from the video feed. So every time this loop runs, and it's an infinite loop, I'm going to be grabbing an image from the video feed and just putting that into a frame buffer. For each frame, I'm going to pass it through my inference function, which is essentially my machine learning model. So for every frame it's seen, throw it through the inference function and actually take out a level of result that is essentially an estimate of what it's seen. I'm going to take it's giving me a whole range of results, but I'm just going to take the most probable result and just say, this is the most likely sock it's seen within that frame. That result, I'm going to write up as a JSON payload and push it into an MQTT topic. So that is whatever the image has seen, the frame that's being seen by the video processor, it's run through the classifier, take out the most likely classification result, and put it into an MQTT topic. In addition to that, I want to make sure that I, as a human reviewing the video feed in real time in the browser, I get that text overlay just to show me what the camera has seen and what the inference function has actually returned. So I'm using OpenCV just to do that text overlay. So I get that nice red text in the top of my video feed just to give me an indication of what the camera has seen. So it's the same message being sent to both MQTT and as a text overlay on my video feed. So I've mentioned MQTT a couple of times. It would be worth just highlighting what that is. So MQTT is a lightweight TCP IP protocol, and it's got a small footprint and it requires very low power. So it's perfect for running on a hardware constrained device such as this. And it allows for really short messages. It's a bit like a notice board. So you can actually just poke little messages onto it just to indicate what it's seen. So MQTT acts a bit like a distributed key value store. And we're going to just be passing messages. Every time the camera has seen something, we're going to be passing those messages onto MQTT. MQTT just acts like that sort of distributed notice board. It doesn't know if anyone's bothering to read the messages, and it doesn't have the smarts to do stream level processing. So MQTT is just acting like a bit of an interface between the camera and the next stage of our processing. So the next stage of our processing, we're going to be using Kafka. Now, Kafka is a distributed streaming platform, and it allows us to store all of these messages over time and do some detailed analysis of them. So although we might be getting messages many times a second from the camera, those messages are just being stored very briefly in MQTT. I want to store all of the history of those messages, and I'm going to be using Kafka to store that long time-ordered sequence of events. So there's a few components I'm going to be using out of the Kafka ecosystem. I'm going to be using Kafka itself as a storage mechanism, that platform for handling that real-time feed of messages from the camera. In addition, I'm going to be using Kafka Connect. Kafka Connect is a framework that allows you to get data from other systems, such as a database, or in my case, an MQTT endpoint, and lift it into Kafka. So I'm going to be using Kafka Connect's MQTT source that will allow it to automatically get all of the messages that have ever been posted to MQTT and put that in Kafka. And again, that means that the messages that were going to disappear from MQTT, I get to keep the history of all of those messages into Kafka. And the last bit of the puzzle is I'm going to be using something called KSQL DB, which allows me to build real-time streaming systems with a SQL dialect. I could write it in another language, but I find KSQL a straightforward way of just emitting my intent using SQL instead of having to get down in the weeds of doing stream level topology in Kafka itself. So those are the bits I'm going to be using. So let's think through one of the first problems I had. The DeepLens image classifier works really, really quickly. I get between 3 and 5 images recognized every second. But at the end of the day, not all of these images classifications are correct. I'm going to give you an example of what happens when I hold up this sort of colorful sock in front of the lens. As that passes through, firstly, I get a whole bunch of blank messages. But the very, very first message that I get, and you can see it here at 18:10:52, is actually incorrect. It's actually being incorrectly identified as a Mongo sock. Maybe there's a bit of green that's just sort of entered the frame. And as this sock moves across the frame, I get a whole series of correct classification messages. I get 7 or 8 messages that are actually correctly identifying this as a Google colored sock. And as it's leaving the frame, you'll see essentially an incorrect message. You'll see a very brief message saying it was a Mongo sock. So you can see that this is essentially going to be a problem. I've got incorrect messages mixed up with correct messages. And even when I've got correct messages, I end up with the same message multiple times. And again, that time sequence on the side just gives you a bit of an idea of the throughput of these messages. I'm getting these message events up to 5 times a second. So my goal is to find messages within a given time window and actually clean it up. So back to this mental diagram, I've got many messages within a short length of time, and then a gap, and then many more messages. And then occasionally I've got these sort of sporadic messages I want to drop out because they're incorrect. So my goal might be, how do I find 4 or more identical sock messages in a rolling window of time, say a 5-second window of time? I want to group arriving images into these windows and bucket them and find the most prevalent image seen. For example, can I identify an image classification that is legitimate because it appears 3 times within a 5-second window? Now, KSQL allows me to express this using this sort of tumbling window syntax. This allows me to just say, what is the most prevalent image that has occurred in a bucket of time, a constant rolling 5-second trailing window? And if I've seen that image 3 or more times within that 5 seconds, promote it out and actually emit that as a change event into a next stream. So I'm building up myself a stream. I'm calling it sock stream smooth, just to take away all of the noisy messages, get rid of the sporadic messages, and actually just emit the messages that have occurred with a level of more than 3 times within a 5-second window. And this clean stream allows me to eliminate all the rogue messages and just clean up my stream. And it also allows me to eradicate messages like blank, which is essentially just photos of a wall that I want to get rid of. This allows me to get onto the more meaty problem of, how do I actually find pairs of socks over time? So now I've got a clean, crisp payload. This is actually a time where I can write another KSQL thing just to say, when I found a sock, where is its matching sock? So that's the SQL dialect, but this might be a bit easier to understand. So if I'm holding up a blue sock, and then a green sock, and then another blue sock, I want to be informed that the second blue sock should match the previous blue sock. And so this dialect allows me to build up a level of visibility on when a sock has been identified, clean up those sporadic messages, build out a much more confident sense of which sock has been seen in the stream. And these higher level constructs allow me to accurately identify, has this sock been first seen, in which case it's not a pair yet? And if it has been seen, where is its paired sock If I've got a pile of socks on my desk, where in that pile of socks should I be able to identify its matching sock counterpart? So that's a lot of technology. Let's see how it looks in reality. So here's a quick demonstration of what this looks like when it's all assembled together. I'm holding up a sock. It's being identified by that inference function in the DeepLens. The DeepLens is writing that payload into MQTT, and ultimately that same payload is going into a platform stream into Kafka. That series of unordered events is being cleaned up, and so when I've got matching events, it is being promoted to a secondary stream. When I've got that clean, crisp feed of sock messages, I can then identify which sock has a matching sock within the sock pile. So that was a large amount of territory. So let's just cover off, what did I learn in this project? I learned that AWS DeepLens is super cool. The object detection is a stream of events, and that even when you've got this up and running, events at the end of the day can be extremely messy when dealing with machine vision. But I also learned that IoT architecture with Kafka and some of the Kafka frameworks is really, really scalable. I also learned that sorting socks does not make you interesting at parties, so it's best to find another hobby when we all return for our next barbecue. And with that, I might open it up and ask, are there any questions? Thanks very much for your time.